Chapter 5, Friction. Friction covers the laws of friction, the drag force and the terminal speed, uniform circular motion. You can find them in a timeline. The laws of friction. Here we deal largely with the frictional forces that exist between dry solid surface moving across each other at relatively slow speeds. This is a situation we deal with. Friction. Frictional forces are unavoidable in our daily lives. If we were not able to counteract them, they would stop every moving object and bring a halt every rotating shaft. About 20% of the gasoline used in an automobile is needed to counteract friction in the engine and in the drivetrain. On the other hand, if friction were totally absent, we could not get an automobile to go anywhere, and we could not walk or ride a bicycle. If you exert a force F on the blocks, attempting to pull it in one direction, say the left, in response, a friction force Fs arises, pointing to the opposite direction, the right in this case, exactly matching the force that you have applied. The force Fs is called the static frictional force. As you increase your applied force, the static frictional force Fs increases also, and the block remains at rest. When applied force reaches a certain value, however, the block breaks away from its intermediate contact with the table at top and accelerates leftwards. The frictional force that then is called the kinetic frictional force, Fk. You want to keep it uniform, it's just very small, keep it equal to 0, okay? Now, let's say the magnitude of the frictional force. This is time, okay? Now, when you apply the force, larger and larger, the relevant frictional force gets balanced with you until you reach some maximum value of F statics, okay? And the body break out. It move instantly. The friction force, kinetic friction force, gets constant and smaller than the maximum one. Usually, the kinetic frictional force, which acts when there's motion, this one, is less than maximum value of the static friction force. Remember, the maximum here is larger than okay, which acts when there is no motion. Basically, the frictional force is a force acting between the surface atoms of one body and those of another. When two surfaces are placed together, only high points touch each other. The actually microscopic area of contact is much less than the apparent macroscopic contact area, perhaps by a factor of 10,000. Nonetheless, many contact points co-weld together. These welds produce static friction when an applied force attempts to slide the surface. When the surfaces are pulled across each other, there's first a tearing of welds to break away, and then a continued tearing apart and the reforming of welds as additional chance contacts are made. The kinetic friction force Fk is the vector sum of the forces at those many chance contacts. Properties of friction. Experiments shows that when a dry and unlubricated body is pressed against the surface in the same condition, and an applied force F attempts to slide the body along the surface, the resulting frictional force has three properties. Property 1, if the body does not move, then the static friction force Fs and the component of F that is parallel to the surface balance each other. They are equal in magnitude, and Fs is in the direction opposite that component of F. Property 2. The magnitude of Fs has a maximum value, Fs maximum, that is given Fs maximum equal to mu Sm, where mu s is the coefficient of static friction, and n is the magnitude of the normal force on the body from the surface. Remember, this defined as maximum force. If the magnitude of the component of the external force F that is parallel to the surface exceeds Fa maximum, then the body begins to slide along the surface. Property 3. If the body begins to slide along the surface, the magnitude of the frictional force rapidly decreases to a value Fk, given by Fk equal to mu k n, where mu k is the coefficient of kinetic friction. Thereafter, during the sliding, the kinetic friction force Fk has a magnitude given by above equation, which is smaller than F, static maximum. We assume in this textbook that the value of mu k does not depend on the speed at which the body slides along the surface. And in any case, mu k is smaller than mu s. This is defined as maximal static forces.
Did you ever wonder why objects slow down and then stop after they're given a push? This glider stops very quickly after it is sent sliding along the track. But when the glider is floated on a cushion of air, friction is nearly eliminated. Now the moving glider slows down only gradually.
Static friction between this wooden block and the table keeps the block from moving until it is pulled by a sufficiently large force. We'll use a spring scale to measure the force required to overcome the force of friction and move the block. In this case, the force is approximately 23 newtons. The force needed to slide the block along the table at a constant speed is less than 23 newtons. The coefficient of kinetic friction is lower than the coefficient of static friction.
Any two objects being rubbed together have frictional forces between them. How do those forces depend on the area of contact between the objects? We'll use this long board and a spring scale to find out. If we pull the board along the table with its widest face down, the amount of force required to overcome static friction is about 12 newtons. If we now tip the board up on its edge so that the surface area in contact with the table is decreased about 4 times, how much force will be needed to move the board? The force remains about the same. To a good approximation, static frictional force does not depend on the area of contact. How does the friction between two objects change as the force pushing them together is increased? We'll use this long board, a spring scale, and some weights to find out. If we pull on the board with the spring scale, we will notice that the board always starts to slide at about the same force. This is the maximum value of static friction. If we add enough weight to the board to double the overall weight, how will the required force change? The force needed to move the board approximately doubles. If we now add another weight equal to the weight of the board, tripling the original weight, we see that the force is approximately tripled.
Simple. If a car wheels are locked, kept from rolling during emergency braking, the car sliding along the road, the skid marks on the road reveals that co-wetting occurred during the sliding. The record for the longest skid marks on the public road was reportedly set in 1960 by a Jaguar on the M1 highway in England. The marks were 290 meters long. Assuming that μk equal to 0.60 and the car's acceleration was constant during the braking, how fast was the car going when the wheels became locked? Now, we analyze the car. It has three forces acting on it: gravitational force, normal force for the ground, and the friction force backwards. Okay, and the situation is it is constant acceleration. So finally it is stopped after 290 meters. This is V0. Okay, is we want to find. Okay, so it's constant acceleration. So we have this formula: v squared equal to v0 squared minus 2ax. And this finally stopped. So this is 0. Okay, this v0 is what we want to find. We know d, so we want to find the ax. Okay, and the ax is from the friction, and this friction is related to normal force. So in this case, vertically we don't have any motion, so n minus mg equals 0, and the friction is mu n, is mu ng. Okay, now in this case, remember, normal force are not defined to mg. Sometimes it is not equal to mg, but in this case is equal to mg. Now we can find f. Okay, and f equal to ma. So we can find a. So a, m cancel out, is mu kg. And we put the a inside, we get a v0. That's very simple. Senior high school calculus. Okay, this is about 58 meters per second, 210 kilometers per hour. Sample. In figure, a woman pulls a load sled of mass m 75 kilograms along a horizontal surface at constant speed. The coefficient of kinetic friction mu k between the runners and the snow is 0.10, and the angle phi is 42 degrees. So how many forces acting on this sled? Gravitational force, normal force, friction, and the pulling force. 4, right? So under these forces, the sled is moving at constant velocity. That means no acceleration. That means the sum of these forces equal to 0. Question A. What is the magnitude of the force T on the sled from the rope? We look at the free body diagram of sled. 4 forces acting on it. Okay, gravitational force, normal force, tension, and friction. So we see horizontally T cosine phi minus friction equal to max 0 because it moves at constant velocity. Ax equal to 0. Vertically see T sine phi plus m minus mg equal to 0 because no motion along this direction at all. Then we see we have T, Fk, and 3 unknown. 2 equations is not enough. We need one more equation. That's a relationship Fk equal to nu n. Remember, you look at this one. This is from this equation, n is not equal to mg because we have T there. So remember, this is definition. Okay, definition is not equal to mg. Okay. Now, this equation we can solve 3 unknown. That's physics. I'm done. The leftover is junior high school algebraic. Okay, look at the T. We can calculate everything. Okay, the upward pull on sled reduces the normal force to 92% of the weight, 3 and 6. Question B. If the woman increases her pull on the ropes so that a T is greater than 91 Newton, is the magnitude Fk on the frictional force greater than, less than, or the same as in question A? Now we see, by definition, the friction force equal to mu normal force. And the new normal force in this case is not equal to mg, equal to mg minus T sine phi. If T increase, N decrease, F decrease. So the conclusion is T greater, the friction force Fk less. Sample. Figure shows a coin of mass m at rest on book that has been tilted at angle theta with the horizontal. By experimenting, we find that when theta is increased to 13 degrees, the coil is on the verge of sliding down the book, which means that even a slight increase beyond 13 degrees produces a sliding of coil. Let's analyze the force acting on the coil. This is a gravitational force downward, friction along the slide, and normal force perpendicular to surface. Okay. The coin is at balance, is on the verge of sliding down. What is the coefficient of static friction mu s between the coin and the book? We know the friction force equal to nu s n. You want to find this one, we have to find this and find this, right? Now we look at the free body diagram on the coin. It has gravitational force downward, friction force along the line, normal force perpendicular to the surface, right? So under these 3 equations, it's in equilibrium. So sigma f equal to fg, fs, n equal to 0. This is a vector equation, so we take it, divide it into x direction and y direction. This is a reference vertex. This is orange, x up, y is up. Okay. So fg, fx is friction minus mg sine phi equals 0. Vertically, n minus mg cosine phi is 0. And from this equation, I get Fs equal to Fg sine theta, M equal to Fg cosine theta. And then you see, we divide each other, we see the mu. Mu is Fs over N. We divide this one, we cancel off Fg, is sine theta over cosine theta, tan theta. We know angle 13, so we find the mu.
This incline has 4 different surface materials: rubber, wood, sandpaper, and Teflon. Identical brass blocks are placed on the 4 surfaces. Now the board will be tilted until each of the blocks starts to slide down. As the board is tilted, the blocks begin to slide in a definite order. We'll repeat this sequence with the angle of tilt displayed next to the board as each block slides. Here are the angles at which each of the blocks started to slide on the various surfaces.
The drag force and terminal speed. A fluid is anything that can flow, generally either a gas or liquid. When there is a relative velocity between a fluid and a body, either because the body moves through the fluid or because the fluid moves past the body experiences a drag force D that opposes the relative motion and points in the direction in which the fluid flows relative to the body. Here we examine only cases in which air is the fluid. The body is blunt like a baseball rather than slender like a javelin, and the relative motion is fast enough so that the air becomes turbulent, breaks up into swirl behind the body. In such cases, the magnitude of the drag force D is related to the relative speed V by an experimentally determined drag coefficient C, according to D equal to half C rho A V squared, where rho is the air density mass per volume. A is effective cross-section area of the body, the area of a cross-section taken perpendicular to the velocity v. The drag coefficient C, typically value range from 0.4 to 1.0, is not truly a constant for a given body because if V varies significantly, the value of C can vary as well. Here we ignore such complications. When a blunt object falls from rest through air, D gradually increases from 0 as the speed of the body increases. Going down, you have the drag force D, proportional to the V. Okay. I suggest in the figure, if the body falls far enough, D eventually equal to the body's weight, Fg mg. And the net vertical force on the body is then 0. By Newton's second law, the acceleration must also be 0 then. And so the body speed no longer increases. The body then falls at constant terminal speed, Vt, which we find by setting D equal to mg in above equation. Terminal speed Vt, Fg minus D equal to ma equal to 0. And this D is half C rho A Vt squared. Okay. So this way we find Vt. Vt equal to mg 2 over c rho 8.
We all know that very light objects, such as this piece of paper, appear to fall slowly. But is the slow descent caused only by their light weight, or is there some other reason? If we crumble the piece of paper into a tight ball and drop it next to a flat piece of paper, the difference is clear. There is more air drag on the larger surface of the flat paper, slowing its descent.
We are used to seeing light objects fall more slowly than heavy objects. But why do light and heavy objects fall differently? We will use this pair of tubes containing metal and paper discs to show the effect of eliminating air resistance. This is how the objects fall when the tubes are filled with air. If we now remove most of the air from the tubes with a vacuum pump and repeat the demonstration, the results change dramatically.
Have you noticed that objects tend to move more slowly through a viscous liquid such as glycerin? We'll drop various balls into this tube of glycerin to see how quickly they sink to the bottom. For comparison, here is how a glass ball falls in air. Here is the same ball falling in a tube filled with glycerin. It falls much more slowly. Here is a heavier steel ball falling in glycerin. Here is a still heavier lead ball falling in glycerin. Here are all three balls falling side by side.
Sample. A raindrop with radius r 1.5 millimeter falls from a cloud that is at height h 1200 meter above the ground. The drag coefficient C for the drop is 0.60. Assuming that the drop is spherical throughout its fall, the density of the water, raw water, is thousands of kilograms per cubic meter, and the density of air, raw air, is 1.2 kilograms per cubic meter. Question A. What is the terminal speed? By formula chemistry, 2 mg over square c rho. We put the number inside. Okay. The m of the ball is volume times rho. Okay, is water, and the volume of the sphere is 4 pi cubic r over 3. And the area, cross areas, are pi r squared. C is 0.60. And the radius r, this r is 1.5 millimeter, is 1.5 times 10 to the minus meter. And the raw air is 1.2 bricks. And the raw water is thousands of kilograms per cubic meter. All these one we put in the formula. Okay, you get an answer. That's very straightforward. Okay, about 7.4 meter per second and 25 kilometer per hour. Question B. What would be the drop speed just before impact if there were no drag force? Then we know V equals square root 2gh. That h is 1200. Okay, so If without drag force, it would be 153 meters per second, much larger. Uniform circular motion. This is a uniform circular motion. When a body moves in a circle or a circular arc at constant speed v, it is said to be in uniform circular motion. Velocity magnitude does not change. The body has a centripetal acceleration directed toward the center of the circle. A constant magnitude given by A is v squared over r. They call it centripetal acceleration. Why the speed is constant and it has acceleration, it seems contradicts to the Newton's second law. Now, we know velocity is a vector. It has magnitude and direction. In this uniform circular motion, the magnitude does not change, constant, but the direction changes. So v changes, you have acceleration. This acceleration, in this case, as we call it, centripetal acceleration equals v squared over r, where r is the radius of the circle.
This spinning disk and a dropper of colored water will be used to show one effect of circular motion. The tracks are tangential to the circle at the points where the water droplets left the disk.
This centripetal acceleration is caused by centripetal force that acts on the body and that is directed towards the center of the circle. The magnitude F of these forces is constant and is given by a Newton's second law as F equal to ma. A is centripetal acceleration, v squared over r. It can be tension force, a gravitational force, or any other force as a centripetal force. Two familiar examples of uniform circular motion. 1. Running a curve in a car. The centripetal force that causes the motion is a frictional force exerted by the roadway on the tires. This force points radically inward and spread over the 4 tires. 2. Orbiting the Earth. The centripetal force that keeps you and the shuttle in uniform circular motion is the gravitational attraction of the Earth for you and the shuttle. The difference is due to the nature of the two centripetal forces. In the car, the centripetal force is a contact force exerted by the road externally on the tires of the car. In the shuttle, the centripetal force is a volume force due to the Earth's gravitational pull on every atom of your body and on every atom of the shuttle, in proportional to the mass of that atom. Thus, there's no compression on any one part of your body, nor even any sensation of a force acting on you. A centripetal force accelerates a body by changing the direction of the body's velocity without changing the body's speed.
This rubber ball is attached to the end of a long string. When the ball is spun in a circle, an inward force is required to make it move in a circle. If the string is passed through this tube, a weight can provide the inward force needed to produce circular motion. When the ball is swung in a circle of small radius, a high angular velocity is needed to keep the ball from being pulled in toward the center. With a larger radius of rotation, a lower angular velocity is sufficient to maintain a circular path.
This coat hanger has been bent so that the tip points straight back toward the finger supporting the hanger. The tip is filed flat so that with care a penny can be balanced on it. Now watch. A few swings bring the coat hanger up to speed, then over the top. This motorized disc has a small section of vertical wall mounted on the edge. A toy man is held in place on the wall by the magnet attached to his feet, which is attracted to another magnet on the outer side of the wall. Now we spin the disc up until the outer magnet flies off. The man remains standing on the vertical wall, as seen in this slow motion segment. When the motor is switched off and the disc slows down, there is a critical speed below which the man no longer stays on the wall.
When water is poured into a bucket, and the bucket is turned upside down, the water falls out. Is there any way to keep water in an open bucket that is upside down? If the bucket is spun in a vertical circle at sufficient speed, the water stays in even when the bucket is upside down.
This spoked wheel is made of flexible rubber. We'll spin it at high speed to demonstrate the effect on the diameter of the wheel. As the speed of the wheel is increased, the wheel stretches outward. When the speed is reduced, the wheel returns to its former size.
Sample. In 1901 circus performance, Allo Daredevil Diavolo introduced the stunt of riding a bicycle in a loop-de-loop, this loop-a-loop. Assuming the loop is a circle with radius of 2.7 meters, what is the least speed v Diavolo could have at the tops of the loop to remain in contact with it? We want to find the velocity here. Okay, so he contact with the loop, otherwise he would drop. Let's analyze the free body diagram at the top. At the top, it was exert two forces. One is the gravitational force, Fg. One is the normal force from the loop. Okay, and it has acceleration, centripetal acceleration downward toward the center, right? So that's very easy. This is n plus mg equal to ma equal to mv squared of r. We see that the velocity larger, the n larger, it changes, okay? So the least velocity is n equal to 0. In this case, the bicycle is just leaving the loop, okay? So least velocity means n equal to 0, and when you see the v equal to r at mg, okay, to mg, and so we get the v equal to gr squared root. We put the number inside, 5.1 meter per second. It's not difficult. As long as you have the courage, you can do it. Sample. Even some seasoned roller coaster rider blenches at the thought of riding the rotor, which is essentially a large hollow cylinder that is rotated rapidly around its central axis. Before the ride begins, a rider enters the cylinder, so a door on the side and a stand on the floor, okay, up against a canvas-covered wall. That means canvas, you have a large frictional coefficient. As the cylinder begins to turn, okay, the door is closed. Okay, the rider, wall, and the floor move in unison together. When the rider's speed reached some predetermined value, the floor abruptly and alarmingly fall away. The rider does not fall with it, but instead is pinned to the wall while the cylinder rotates, as if an unseen and somewhat unfriendly agent is pressing the body to the wall. Later, the floor is eased back to the rider's feet. The cylinder slows, and the rider sinks a few centimeters to regain footing on the floor. Some riders consider all this to be fun. Suppose that the coefficient of the static friction μs between the rider's clothing and the canvas is 0.40, and that the cylinder's radius r is 2.1 meter. Question A. What minimum speed v must be cylinder and the rider have if the rider is not to fall when the floor drops? We see that vertically you have friction and gravitational force. You stick on there, don't fall, that means you're zero. In that case, we see the normal force should be mv squared over r. That's actually centripetal force of it. Okay, and the v, you know that equal to rg over mu. Stick from here, we can get this one. Okay, because n equal to this one, they put aside, we get this one. Okay, we put a number inside, we get a number. Question B. If the rider's mass is 49 kilograms, what is the magnitude of the centripetal force on her? That is equal to mv squared r. We have a v, we have m, we have r, we get a pretty large one, 1200 Newton. Next lecture, Chapter 6, Kinetic Energy and Work. Welcome you make a comment and give suggestions so that this program can be more helpful. Acknowledgement. This video clip is a part of my lectures on college physics during 1990 to 2021, based on the adapted textbook, Principles of Physics by Holliday, Resnick, and Walker, published by Wiley. The demo videos were bought from a company in USA by my university for teaching. They help a lot. I'm sorry for not remembering its name to show my appreciation. It seems that they came from the University of California, Santa Barbara, where I got my PhD in physics. Thanks God.